For vector calculus, let's begin with an appendix, vectors and the geometry of space as preliminaries. In vector calculus, you'll be frequently asked to deal with vectors and various geometric objects in two-dimensional and three-dimensional spaces. In this appendix, we'll review vectors and equations of 3D geometric objects. Here we have section 8.1, vector operations. From high school, you learned how to get the distance between 2 points in the plane. These 2 points are in R2. Then the distance between these 2 points is formulated in this way. By using the Pythagorean theorem, you can get it. This formula can be easily expanded for points in 3D. Now, PQ are given in this way. Then the distance between these 2 points is formulated in this equation. It has only one extra component, and so that you can easily understand that, of course, this one is also obtained by using the Pythagorean theorem. Try to solve this problem by yourself. A circle is defined to be all of the points in the plane that are equidistant from a central point. And again, this one is obtained from the Pythagorean theorem. Okay, once there is a circle, then here, now, if we choose an arbitrary point on the circle, then we can write down that is x and y. Now, equation of a circle is basically a relation between x and y. Now, circle is defined in this way, so that there is center, that is A and B, and now distance from AB to XY is R. So if we try to draw a right triangle, then this distance will be here x minus a absolute value, and height must be absolute value of y minus b. So that by using the Pythagorean theorem, we can reach that equation squared. Squared summation must be r squared. Again, this formula can be expanded easily for the equation of sphere. And by using the Pythagorean theorem, we can reach that one. The center is HKL, and a point on the sphere is XYZ. So by using the Pythagorean theorem, we can get this one. Show that the equation is, this equation is the equation of a sphere, and find its center and radius. Once you are dealing with circles or spheres, then the major components are the center and the radius. You have to, in most cases, you should start with finding these two major components, the center and the radius. Let's do it for this equation. Okay, to show this equation as an equation of a sphere, we may try to change this equation into this standard form. Okay, let's consider x terms. Then that is x squared minus 4x. And how about y terms? This r plus y squared and plus 2y. And now z terms, they are plus z squared minus 6z. Okay. We have to now deal with that one. However, also to make this term and transform this term in a perfect square form, we need here 4, constant 4, and for this one we need 1, for this one we need 9. Now 1 and 9 will become 10, but a 4 is added extra, so we have to add 4. Then this equation and that one must be the same, right? Okay. Now from here, this one will make x minus 2 squared. And this portion will make here y plus 1 squared. And the last portion will make z minus 3 squared. And right side is 4. Of course, 4 is 2 squared. So we found here the center is 2, minus 1 and 3. And R is 2. And of course, the given equation is the equation of a sphere. Okay. Vectors and vector operations. A vector is a mathematical object that stores both length and direction. If there are 2 points in 3D, then the vector start from P to Q can be defined in this way. Basically, this vector is same as Q minus P, but we are using here notation OP, OQ to indicate that is a position vector. But here, this one is the same as Q minus P. So that is the vector start from P and ending at Q. Two vectors are equal if and only if they have the same length and direction. The vector has 2 components. The length and direction, they are the same, then vectors are equal, no matter where it begins. For vectors in 3D, the magnitude or norm or length is defined in this way. And that is, again, by using the Pythagorean theorem, it is defined. And xyz coordinates, and v is given in this way. Then start from here to there, and that is a vector v. Then by using Pythagorean theorem, now that is a square sum and square root. So that is exactly the length. But sometimes we call it norm or magnitude. Vectors are mathematical objects like the natural numbers, whole numbers, integers, rational numbers, and irrational numbers, all real numbers. And like that, vectors are also mathematical objects, so we may define addition, multiplication, or subtraction, division. But vectors have 3 components, so that it's not so much flexible with elementary operations. Here, we start with a vector addition. There are two vectors, u and v. Then the vector addition is defined in this way. Component-wisely, the terms are added. First component from u and the first component from v. That makes here, addition makes the first component of the addition. In the same way, for these are from second components, these are from the last components. Here we have scalar multiplication. And for given vector and constant k, scalar k, here kv is obtained with this formula. For each component, we multiply k. That is the definition of scalar multiplication. Okay, for this problem, here, okay, you can find, for example, length of A quite easily. That is the square root of the square sum 0 squared plus 3 squared plus 4 squared. 9 plus 16, so that is 25. So it is 5. Okay. Now 2a minus 3b. Okay, that is 2a minus 3b. That is 2. Okay, we try to write down that one as a vertical vector. 0, 3, 4. Minus 3 times, again, vertically. 1, 5, 2. Then, this scalar product is now scalar multiplication is making 0, 6, 8. For the second one, the product will make here 3 and 15 and 6, right? Okay. So now we defined only vector addition, but subtraction can be defined the same way. So here, component-wisely, we subtract. So the first one will become minus 3, second one minus 9, and the final one must be 2. That's the result. And again, the length of this result can be easily obtained. Square sum and take a square root. Then that's the final answer. A unit vector is a vector whose length is 1. So in many cases, for given vector, you may try to find a unit vector in the same direction. And once a vector is non-zero, v1, v2, v3, then unit vector, length one vector in the same direction can be defined in this way. Just try to divide by its length, then eventually the resulting vector should have length 1. So it is a unit vector in the direction of v. Any vector can be denoted as a linear combination of the standard unit vector I, j, k. I is the standard unit vector in the first coordinate direction in x direction, that is in y direction, that is in z direction. So therefore, given vector, you can write in this way, and quite easily you can check here, right? Here we have the definition of dot product for given two vectors in 3D, v1, v2, v3. U is u1, u2, u3, v is v1, v2, v3. dot product u dot v is defined in this way. Component-wisely multiply and then sum. That is the definition of dot product. This dot product is called sometimes inner product or Euclidean inner product. And once you try to make dot product with itself, so the v dot v, then that one must be v norm squared, right? For two vectors, now theta is the angle between the vectors, then the dot product between the two vectors can be written in this way: u norm, v norm, and cosine theta. This formula will be used quite frequently. And sometimes this one is used for the definition of a dot product. Two vectors u and v are orthogonal if and only if u dot v equal 0. Orthogonal means that geometrically it has 90 degrees. So that if they are orthogonal, then here cosine theta, cosine pi of 2 will be 0. So that dot product is 0. And for dot product, we have this formula now, so that here there must be 0, or one of them is 0. But any case, here once a vector is a 0 vector, then the vector is always orthogonal to every other vectors by definition. Okay. Okay. Find the angle between the vectors A and B. Okay, we'll try to use this formula. First, we try to get A dot B. Okay, that one is 2, 3 multiplication is here for the first one. From second components, 2 times 0. And from the third components, and 1 and 3, right? 2, 3, 2, 0, and 1, 3. Okay. So that is 6, that is 3, so that is 9. Okay, what is the norm of A? That is square root of 2 squared plus 2 squared plus 1 squared, which is 9, so that is 3. And how about the norm of B? That is square root of 3 squared plus 0 squared plus 3 squared. That's 18. So the square root of 18, and 9 times 2, 3 square root of 2. Right? So by using these components, we can write here 9 A dot B. 9 is the same as 3 A norm, and B norm is 3 square root of 2 and cosine theta. Right? So from here, 9 will be cancelled and divided by square root of 2. We can reach at here 1 over square root of 2. From this one, we can conclude that theta is pi over 4. Right? Okay. Now we'll define cross product for two vectors. The cross product is defined to be the determinant of the matrix. U cross V is determinant of ijk, the standard unit vectors, and u vector, v vector. And here, by using the cofactor expansion, we reach this one. And so that by taking the determinant from each one, we reach at that one. In most cases, this last one is defined to be the cross product. But this one is a kind of a computational technique. Rather than trying to memorize this one, you may try to use this formula to get the cross product. Let's try to do here. Okay. Now, A cross B is the same as, okay, now, okay, same as, now determinant of matrix I, J, K, and A vector 1, 3, 4, and B vector 3, -1, -2. So from this one, now along with I and minor, okay, that is now a determinant of this matrix -1, -2. Now, minus J and determinant of the corresponding minor after eliminating row and column of J, and remaining part is 1, 4, 3, -2. 1, 4, 3, -2. And then you have plus K and determinant of the corresponding minor row, column, eliminated, and the remaining part is here 1, 3, and 3, -1, right? Okay. So yeah, from this one, I, so it will be first component, and determinant will be this product minus that one, and -6 minus -4, so that is -2, and -2, -12, -14, but we have a minus here, so that +14. And now for this last one, -1, -9, -10, right? So that's the cross product. The vector A cross B is orthogonal to both A and B. And the cross product, okay, you can easily find this one. In fact, that one has a formula in this way: A dot A cross B, that is 0. You learned this one from some other, in other classes anyway, like that, right? Okay, for two vectors, if theta is the angle between the vectors, then now the cross product length is the same as norm of A and norm of B times sine theta. Is well-known formula, and also we'll use this one a few times in vector calculus. Okay, the length of cross product is equal to the area of the parallelogram determined by A and B. It's a kind of geometric interpretation of cross product. Now, vector B and vector A has angle theta. Then, for this one, we can make a parallelogram And now this, if we consider B as the bottom of the parallelogram, then the height can be decided in this way. The length of A times sine theta. So that height is given this way. So that this multiplication is exactly same as the length of the cross product, right? So this is a kind of a geometric interpretation of the cross product. Prove that two non-zero vectors A and B are parallel if and only if A cross B equals 0. By using this formula, you can easily find that if they are parallel, then the theta will be 0 or pi. So either way, in either case, the sine theta will be 0, so that the cross product must be 0, right? So you can easily check this one by using this formula. The cross product is defined as a vector that is perpendicular to both A and B with the direction given by right-hand rule. And if this finger, that is in index finger is A and middle finger is B, then your thumb is A cross B. And by using this right-hand rule, the cross product is determined. In fact, you may try to, you may think of this one as the definition, and you can easily find the direction of cross product. Of course, always the cross product is orthogonal to A and B, but the orthogonal direction can be this direction or down direction. But by using this right-hand rule, you can see that cross product is the thumb direction. Okay? Okay, that's the end of the section. Thank you.